Welcome everyone. It's my privilege to introduce today's speaker. Scott Mensing is a recently retired paleoecologist. Is that the coolest title ever? And a local native, and he's going to talk today about the landscape of our prehistoric coast. Welcome, Scott.
Thank you very much. Thanks for coming. This is a phenomenal crowd, and thanks to Elizabeth for reaching out and inviting me to do this. I grew up in San Anselmo, and so I'm quite familiar with the area, but I spent my career up at the University of Nevada, Reno, and so a lot of my research has been in other places. But even from there, I brought field trips down along the coast, and so over time I've studied something of kind of the origins of the landscape here, but I kind of had to learn more in order to do this talk, and so I'm sure I'm going to say something and one of you will go, I don't think that's right, I know more than he does, and that'll be true, right? And you'll have been to some of these places that I'm going to talk about, and you'll know them better, and so I encourage that for like questions and answers. Also, anytime you talk about paleo, you're going back in time, sometimes a long way, and there's no pictures of that. And so it has to get represented through diagrams and figures and data. So there's a little bit of squiggly line kind of science data stuff in this. And so anywhere along the way, if I'm using a term that just like makes no sense at all, or I've breezed over a graph and it's like, I'd actually like you to explain that a little better, just holler out. That's not a problem whatsoever. I'm going to speak across kind of three different kind of approaches here. The first one will be geologic type evidence, largely because it takes the longest for the land to actually set up the way it is. Geology is a fairly slow process. It takes a long time for these things to spin out. So the first thing we're going to do is talk about the land that we actually walk on and the setting that everything takes place on and its history. Then I'm going to move into some of the climate history, which happens on shorter timetables, but it produces equally dramatic types of differences. And the very last piece that I'm going to talk about in the third section is the fauna and flora that essentially are the most ephemeral elements of our landscape. They're often the most obvious to us because we're walking out in the woods and this kind of a thing. But they're the shortest. They change the most rapidly, and so that'll kind of be the progression of the presentation. So I want to start with a pattern here. If we look at this map, this is a geologic map for the area. It's very similar to the geologic map that we have posted up here. The black line here represents the San Andreas Fault, and we happen to live in a really intriguing and interesting geologic and climatic region. And to one side, you'll notice, even from the back of the room, that it's pink and orange. And on the other side, you're going to notice that it's mostly this kind of olive green with a little bit of blue. These represent completely different rock geologic histories. And so the first part of this talk is, how did this get to be? How did these get to be the way they are, and what's the significance of that? These pinks over here, these are all granites. Granites are formed deep under the earth over millions of years and take a very long time to get here and up to the surface. Everything over here is oceanic. It's called the Franciscan complex, or the Franciscan melange. And it's a whole combination of things that were created in the sea. And so how did we get this juxtaposition? This orange is also marine. This is also in the sea. But how did we get this juxtaposition of these granites here and all this oceanic divided by the San Andreas Fault? Completely different kind of rock types. That's where we want to start. Here's simply another view of that. If you take a slice of the earth and you're looking just across it, here's an example. This is Bodega Head. This is all granites. Here's our San Andreas Fault running through here, and this is all marine. And so if you were to slice the earth, you'd notice that on this side, it's a completely different geologic structure that's attached than it is on this side. This is the Pacific plate. This is the North American plate. They're separate, and they have a distinct history. And so this is all this Franciscan, oceanic, and these are these igneous granites. And we're familiar with these. When you go out to Point Reyes, it is sitting on this granite. Cretaceous, 82 million years old. And that's what it's sitting on, right there out on the coast. Here's what it looks like. If you go up to Bodega Head, it is the same granite, Cretaceous, 82 million years old. This gray that's down here that we see up there on the head. If you go down the coast a little bit to Point Lobos in Monterey, it is also the same Cretaceous granite. It's the exact same rock in all these different places, just hunkering on the edge of the coast. There's a really interesting story about how this came to be. It's very different. You do not see this anyplace else in California. It happens that these are part of a geologic block called the Selenian block that was formed in the period of about 80 to 100 million years ago, far to the south, and it sits now completely on the west side of the San Andreas Fault. But what's even more interesting here is when we think about the San Andreas Fault, it is not just one fault line. It's a whole series of fractures in the earth that step from the east across to the west. And one of these is the San Gregorio Fault that actually falls all the way out here, right on the edge of the coast. And if we look at Point Lobos, Point Reyes, Bodega Head, they're not just on the west side of the San Andreas Fault, they're also on the west side of the San Gregorio Fault. And so the question is, how did these little tiny pieces of rock end up where they are? They all started from the same place, but now they're stretched up and down the coast, and they form a really interesting history for kind of what we have here. In order to know that, we have to step back about 50 million years. So when we're talking about the landscape, you have to kind of look across a broad section, and you have to go across a vast amount of time in order to explain what we see today. And in this case, we have to go back and we have to look at the kind of plate tectonic history of this area. So, at that time, and now we're actually back 100 million years. At that time, there was a plate out here that was called the Farallon Plate that was subducting underneath the North American Plate. And this on this side is the Pacific Plate. The Pacific Plate still exists today. The North American Plate still exists today. The Farallon Plate exists in a much smaller portion, and it's called San Juan de Fuca or Gordo Plate, and it's pushed up to Northern California, Oregon, and Washington. But it doesn't exist in this configuration at this time. So what's happening is these are separating, and this plate is diving underneath that one. It's denser, it's thicker. And so when they collide, because they're pushing into each other, one goes underneath the other. And that creates some really interesting phenomena. These ones are pushing apart. That creates a different phenomena. We'll talk about this pushing apart here first, because there's some cool stuff near Nicosia where you can see this. This pushing apart, there's magma coming up to the surface of the earth. Okay? This diving down, there's rock going deep underneath. So where it's going deep underneath, as it goes down, it gets really hot, the pressure increases, it melts. Some of it stays down here, but some of it finds cracks in the earth and starts working its way back up. Some of it comes all the way out as volcanic rock, but a vast amount stays molten deep in the earth, and it cools there very slowly. That's where Point Reyes started. That's where Bodega Head started. That's Point Lobos, okay? But it's had 80 million years to move from being here to being down the road from us. So, the granite's forming down here. This is all then ocean out here, and the plates are pulling apart up here. Where they're pulling apart up here creates kind of an interesting thing, so I'm going to do just a quick side detour to talk about that. It creates these things called pillow basalts. And so this is pulling apart, magma's coming up, but it's coming up under the ocean. And so when it comes out, it's very hot, but it goes immediately into very cold water of high pressure. And it solidifies quite rapidly into these forms that are only about this big, that we call pillow basalts. How do we know this? Today, we can go down in the ocean and see them, but they're remnants of them right here. So if you go out Nicasio Reservoir and you're driving towards Point Reyes and you get to the sign on the left, Golden Gate National Recreation Area, this is all pillow basalts. And there's a great pull-off just to the right, so you should stop there sometime and get out, watch, because the cars come faster than they should. But you can see these things. And so that mid-oceanic ridge of the Fairlawn Plate eventually moved over kind of into the subduction zone and got heaved up and smeared onto the edge of the continent, and it's now at Nicasio Reservoir. If we go back to talking about these granites, this is our picture of what the continent would have looked like on the order of 50 million years ago. Okay? And so here we are, this is the Fairlawn Plate, this is going on, there's subduction going on, and remember that picture where all of the stuff was melting underneath the rocks, that's over here. That's the Sierra Nevada that are in their initial form, all formed about 100 to 70 million years ago. Out here, all of this stuff is eroding, washing off of the continent, coming down into the ocean. This is called Franciscan subduction. This is where all the marine sediments are being laid in right now. And so it's kind of interesting because, remember in that very first map I showed you that the granites are to the west of the marine sediments. But in fact, they were formed the opposite way. The marine sediments are all over here, and the granites are over there. And so we have to ask ourselves, how did these things kind of reverse their position and get to be where they are? So we'll go through that. In the ocean, this Franciscan complex, which is the bedrock, that kind of olive green that I showed you of much of West Marin and West Sonoma, these are these things called cherts and shales and sandstones and conglomerates. Conglomerates is just like, it looks like concrete. It's just a bunch of gravel that's been cemented together. And that usually comes from these turbidites or these underwater kind of avalanches that come off of the land. It's very steep. They come down in these big chutes and they collect. They become very hard rock. And so in fact, if you go out to Point Reyes, not only is there granite there, but there are these conglomerates there that are very, very old that are sitting on top of the granite. Chert, if you go upstairs and you look at the collection of arrowheads, I noticed most of them are obsidian, but then they say, there's some light-colored ones. Those are all cherts. They're red, okay? And this is from silica that came from very deep in the water. And then shales and sandstones. Sandstone we're familiar with because that's just what the beach would have been. And so we use these different kind of rocks to tell us how deep the water was and how close we were to the shoreline, because the sandstone's all made very close to the shore, and the chert, which is this clay material, comes out deeper. So we use this to kind of reconstruct what the world would have looked like. Here's a diagram that shows kind of where these things are happening. So I had mentioned before, the subduction's going on down here, the granite's being formed over there, over on the continent, and then the coastal areas where all of these marine sediments are being laid down in what we call this Franciscan sedimentary melange. So that's the whole Fairlawn Plate that's going down. Deep down, there's some of the rock is being reworked into what we call metamorphic rock because it gets kind of partially remelted and then comes into a different kind of rock. There's a kind of rock called schist that gets formed down here. And I'm only pointing it out because later I'm going to show you a picture of schist, because when you're driving around, you can actually see these things on the landscape. So all the marine stuff is collecting here, and the granites are over there. This is just the Sierra Nevada today. We can see the whole sweep of the Sierra Nevada. There's California. And note that as the Sierra Nevada comes down, it actually curls around to become the Tehachapi, and it comes all the way over to the Grapevine, which has been in the news a lot lately because they had to close it because of snow, right? That never happens, okay? But note that down here, there's these granites that kind of curl out farther to the east. These are the ones that are eventually going to become our granites up here. So I mentioned the Selenian block. The Selenian block is this group of rocks here. We can see that they're all on the western side of the San Andreas Fault. This is the granites of the Sierra Nevada. These are granites that show up all through the Mojave Desert and even down in the peninsula ranges. It's all similar and sometimes identical rock. And so what we're going to look at is we've got our Bodega Head here, Point Reyes, the Fairlawns. Fairlawns are the same granite rock. And then down here at Point Lobos and other places along here. This stuff all started way down here and has been dragged up. So let's look at, there's going to be a series of kind of geologic, historic maps to kind of show our reconstructions of how we think this happened. So if we go down 50 million years ago, most of the California was actually deep ocean. It's not too easy to see. It's not bad with this projector, but you can see they've put out the kind of boundaries. And so that's where that's Monterey there. San Francisco is right in here. That's Point Reyes right there. That was all out in deep water. And so 50 million years ago, this was all under ocean. And we have this subduction going on. Here we see, this is just a kind of a geologic equivalent of this. This is kind of just your Google Earth picture of what it would have looked like. And this is quite a more your geologist geek picture of what it would look like. Where here's the Fairlawn plate, it's subducting. And that means that the granites are being formed over here. And this is the Sierra Nevada. Here's the original early Sierra Nevada up here. And this down in here is this selenia. These are the granites that we're kind of interested in. They're formed pretty far to the south. So we're just going to kind of play this forward. Now we've moved to 30 million years ago. And this is where it starts to get really interesting, okay? We've still got subduction going on. Not that it wasn't interesting before, but now it gets really interesting, okay? But look at the Fairlawn plate now has disappeared in one place. And so as it's been subducted, okay, it came to the point where there was no more plate to subduct, and now it's bumped up. The Pacific is bumped right up against North America, and they're just butting heads like this. And one says, I'm not going under the other anymore. And so instead they start moving past each other because there's no more subduction, and it gets changed into what we call transform faulting. So instead of one going under the other, now they're moving past each other, okay? This is not the San Andreas Fault yet, but it's the beginnings of that. And that was 30 million years ago. Up another 10 million years. Don't you love geology? You can just move 10 million years like that, right? That didn't take long, did it? Okay? Now you can see that it's starting to widen out, where on the Pacific, it's moving to the north. The North American side, it's moving to the south. Here's our Selenian, and it's moving as part of this block as this kind of swallowing of the Fairlawn plate continues to happen. And we still have mostly ocean out here over most of California. So still, it's nothing like what we see today. Finally, about 10 million years ago, we begin recognizing what we'd call the San Andreas Fault. And so most of the Sierra Nevada and its granites are on that side of the fault, and the Selenian block is on this side of the fault. And because of this kind of action of moving, this is now being transported from its early phase where it was either off of the southern Sierra Nevada or potentially all the way down around Baja. That's not quite clear. But it's now moving in this one unit, like a big RV traveling north to the redwood countries, and it's just moving, shifting its way north. And this, once the San Andreas Fault system is in place, it continues to move. It's still moving. By 5 million years ago, we can see that now this selenium block has shifted up, so the portions of it are all the way up here. This is getting pretty close to where we are today geologically. This MTZ is the Mendocino Triple Junction, and that's where the Pacific Plate meets what now is called the San Juan de Fuca Plate and the North American Plate. That's the end of the San Andreas Fault system. That's kind of in place, and we can see that our rocks are largely there. If we come over and look at the coastline here, it's starting to look a little more recognizable by 5.5 million years ago. Notice that the San Andreas Fault's here, but our coastline, we're still out there. So there's still a lot of marine sediments being dumped off here. And this is where we remind ourselves that while this granite block has been pushed north, the whole time, 50 million years worth of material is eroding and washing off of the oceans, off of the continents into the oceans, creating these marine sediments that have continued to build up this whole time. And so these granites are kind of moving their way north, but marine sediments are coming down on top of them. This will play into kind of what it eventually looks like. Within the last million years, we finally got to being where we are. People are pretty confident that in the last 10 million years, the system, these rocks moved at least 300 kilometers. Some of the estimates are that they moved 500 kilometers, all the way from the Mendocino, from the Mojave area. And so I showed you this before, but this is where Bodega Head, Point Reyes, Point Lobos, these granites that were formed over there in what we think of as Sierra Nevada were sliced off by first the San Andreas Fault and then sliced again by the San Gregorio Fault to finally pull them up into the position where they are today. And so that within the last million years or so, they came to reside kind of where they are. They're still moving, all those faults are still in place, and so they're still on their path. It's just, this happens to be the time when we live here, right? So this is what we see. We live for such short amounts of time that we just get this snapshot of what the world looks like. And so that's what we get. We get the final result of 50 million years of movement creating those headlands. Why headlands? The granites are much harder than the marine rock in most cases, so they're the most resistant, so they're the last to be eroded. And so nearly all of our headlands are very resistant rock, and the granite is one of the more resistant. On top of that granite is a lot of marine sediments still. So as that selenium block drifted north, as I kind of hinted at, there was still a lot of material coming out, and so it had to have kind of collected on top. So if you go out to, say, Kehoe Beach, what you find is that there's marine sediments. This T stands for tertiary. It's about 10 million years ago in this case. And these are all sandstones, cherts, siltstones that are sitting on top of granites. So you walk along, you can see chunks of granite, you can see granite here. These are the things that are sitting on top. How did they get there? As that granite selenium block was kind of pushing its way north, it was off the coast and everything was deposited over the top. In places, millions of years are gone, which meant that everything was getting eroded away until finally some of it stuck and stayed there. But we see this across the area here, that even if you had granite basement, now all that marine stuff that was deposited stays there. In this case, there's about 10 million years of difference. If you go to Bodega Head, here's your 100 million year old and 80 million year old granites, and you have all this marine terrace sitting on top. It's only about 40,000 years old. So everything else there disappeared. So what you have there are simply sands, sandstones, silts from essentially the last 100,000 years that went down and laid on it and have been preserved. Driving around the landscape, depending on which side of the fault you're on, you can see some of the evidence of all this history. And so keep your eyes out and look. We see these resistant rocks left behind that geologists call knockers. And this one happens to be blue schist. It's common on the eastern side of the San Andreas Fault. You're not going to find nearly as much of it over on the other side. It's a metamorphic rock that was formed way down here and then eventually kind of got dragged up in this process and scraped up onto the continent. And you'll find other of these kind of resistant rocks just kind of sticking out. I mean, even just driving in here as you're coming along, there's all these wonderful rocks that just stick out. And you'll be looking at these nice smooth hills and there'll be one that just sticks out. These are all just these old resistant marine sediments that for whatever reason were cemented better, more tightly. They're older, they're metamorphosed in some way, and so they simply resist erosion a little bit more. And when the erosion kind of surface drops down, they protrude and they stay sticking out. The other one that people think about a lot here is elephant rocks. It's the same kind of a thing. These happen to be just a really well-cemented sandstone. Okay? And it's marine, it's old, it's on the eastern side of the fault. You often see granites weathered to look very similar to this. So when I first saw these, I thought, I wonder if those are granites. But no, when you walk over, they're quite clearly sandstones. They just happen to be massive, strong, very few joints, and so they weather in a way that makes them a lot of fun to climb on. These nice and cool looking towers. There's a lot more of this down there, right? The erosion's just going to eventually exhume a lot more of this. And it's simply kind of the same way a granite headland is the last thing to erode. These are going to be the last thing to erode in this landscape unless they stand out. And these are part of that old Franciscan complex of marine rocks. We also sometimes get whole bodies of rock that would come together in these things called terrains. And so we actually get big chunks of the landscape. And here, the estimates are 100 million years ago that the marine headlands were out here. They were on that plate. And you have to kind of think of that almost like the island of Japan or something like that. The island of Japan is sitting on a plate that is moving towards Asia. Someday it's going to be attached. It's the same kind of thing. Marin headlands was attached, and if we go there, we see chert, gray wacky, green stone, serpentine, all of these rocks that are associated either with marine sediments or metamorphism of those. They were formed out here, and as the plate then went over and subducted, they didn't subduct, they simply got smeared on and became part of the continent. That's how a lot of our continent got made. Remember, it was out here, this was all ocean, but over time, more and more of these things got pushed and stuck. So, it's a long story to kind of explain these two different colors, but what we end up with is the San Andreas Fault is the boundary between two really different geologic histories, and we have the granites with some young marine on the west, and we have this Franciscan, which is a really interesting mix of very old, 80 million to 10 and 20 million year old, that's all been mixed and kind of dragged up together, smeared on and forming the continent on that side. So that brings us up to the last 2 million years of how the land got there. The next part of the story moves to the climate.
Uh-oh.
I know, this is that first of those deadly squiggly lines, but it's not so bad. Okay, time. This is the present. We're here. We're going back 5 million years ago. That's what that MYA is. This is sea level. Okay, it's not really sea level. We use proxies. This is albedo proxy. We use different methods of kind of testing, reconstructing, figuring these things out. Okay. But for us, what's important here is this is modern sea level right here. And if you look, 3 to 5 million years ago, sea level was at or higher than it is today. That was the standard. And then, for the last 2.5 million years or so, you see that it's lower. And it's sometimes much, much lower than it is today. You know, where did this come from? Well, it turns out that about 2.5 million years ago, the Earth went into a very strong cooling phase. And I know all the conversation these days is about global warming, but in fact, the Earth is much cooler today than it was 3 million years ago. And this was driven, surprisingly, by tectonics as much as anything. At that time, South America had been moving north, and it finally merged with North America. It isolated the Pacific from the Atlantic for the first time in 250 million years. And that changed oceanic circulations and cooled the Earth. And in that cooling, it created ice caps that would sit over the northern hemisphere, very large ice caps. And so this warming period back here became more highly variable and at different times much, much colder. And so when it's very cold, we've had ice ages, and when it's warmer, we have interglacials. If you look, this is the modern today, this is 0, that's us. We live in an interglacial. We live in a period between ice ages. If you live long enough, God bless you, you will see the next ice age. Okay? But they don't come around quite that fast. So, we're grateful. We live in a warm period, but not that long ago it was icy. And it's not just that. What we have to remember is this repeated itself. And so in the last 2.5 million years, we think the evidence is that we had probably about 20 of these ice ages. So the history that I'm going to show you now has been repeated. And when history gets repeated like that over and over again, it gets a lot more ingrained in the landscape. So, how much ice was there? It was 2 miles thick over Hudson Bay, which is why Hudson Bay is Hudson Bay today. It was so heavy it depressed the Earth, and it's still coming back up from that. And so, covered all of Canada, dipping down here into the United States, over Greenland, over into Fennoscandia, up into northern Russia. Okay? And so, it did a couple of things. One, it took sea level way down, and in doing that, it created land bridges. So it created a lot of interesting dynamics. Mostly what I'm concerned about is changes in sea level. And those changes in sea level, we often think that ice ages, it's ice that affected everything. But when you have that much ice, all that water came out of the oceans, and it didn't flow back. And so sea level got dropped 120 meters, and that makes some really interesting changes to coastlines. And the biggest thing is, it's rises and falls in sea level that make our coastal marine terraces. When we drive north along the coast, and we have these nice flat spots, this is taken up along Sea Ranch, these big flat things, they are there because of climate and changes in sea level, combined with tectonics. If you have continuous tectonic uplift and rises in sea level and fall, you create these marine terraces. It's that combination. Sea level is down. So I'm going to show you some pictures here going back in time. This is estimated 300 to 500,000 years ago. Sea level drops, it goes out, but mountains are pushed up, nothing's happening. Sea level now rises, okay? It's one of those interglacials. All that ice melts, sea level comes up, it comes roaring in, and it cuts into and erodes the edge to create these cliffs like we see today. with sea level rise, and everyone who's driven north along the coast here knows, homes on the coast are vulnerable. Why? Because the coast moves back. That erosion is also cutting, flattening off the coastline outside. It's eroding these back, but it's creating what we call a wave-cut platform. And this is Duxbury Reef off of Bolinas. And you go down there, this is what it's doing out there. Okay? It's cutting this thing called a wave-cut platform. There you see a marine terrace, the mesas of Bolinas. So then you go through another ice age cycle. Remember, we went through these 20 different times. Sea level goes down again, it goes out, uplift continues. We get another wave cut platform coming up. Okay, the ice comes back. Sea level comes in, it cuts another cliff. And so you begin to see that we get these stair step in the landscape of marine terraces and cliffs. So this is an aerial view. This is up in Mendocino just because they're so beautiful up there. You can see here's the cliff, sea level's up, it's pushing the coastline back. Here's that was a wave cut platform, but it got lifted up because there's constant tectonic uplift here because, heck, the Pacific plate's pushing against the North Atlantic plate and something's had to give, so it gets pushed up. Here's the previous cliff, here's what was a wave cut platform before. Looks different because there's been 100,000 years of erosion softening that and making curves. But that's what you get from this process of sea level up, sea level down, sea level up, sea level down. So it's not just ice, it's all that water that makes a big difference. When we look out and we see these sea stacks off the coast, just remember that's where the coast used to be. And it's not coming back. What are some of the other interesting things we see? We see fossil ice age sand dunes. This is out at McClure's Beach. This looks like nice soft sand, but if you go up to it, it's all cemented together. Every time we had one of those changes in sea level, okay, the beach, we had a beach there. Those beaches were there over a period of 100,000 years because this whole ice age cycle takes about 100 to 120,000 years. That sand would eventually get cemented together, and in some places it's been preserved so that we essentially have fossil sand dunes. And so this is one of those kind of sources of evidence that we have. This is created because of ice ages. One of the more interesting things that people kind of think about also is the coastline went way out. So about 18,000 years ago, the coastline was out here beyond the fairlines. You could have, animals would have, plants would have walked, traveled to the fairlines. They were not isolated. The Sacramento River simply came down, cut through. Remember, it happened over a period of 2 million years, about 20 times. And so the channel through here is very deep because you have the entire Sacramento River cutting through it each one of those times, carving out these nice valleys and carving out Tomales Bay the same way. So here we see kind of a reconstruction of what that all would have looked like with the Farallon Islands, just kind of hills there. Tomales Bay simply being a valley created by the movement of the San Andreas Fault that would have then channeled. Lagunitas Creek would have kind of run all the way out, come all the way out and drained out to there. I love this painting. This is by Laura Cunningham in her book, A State of Change, where she kind of does her artist renditions. This is San Francisco Bay with no water. Okay? Here's Angel Island. You can see the fog out there. That's the Golden Gate, Mount Tam over there. But it would have just been filled in. It would have had different flora, different fauna. The fauna have changed dramatically. We don't really get to see this when we go out now. Right? This is kind of a shame. It would have been cool. But the trees would have been similar, except under one thing. Here, during the Ice Age, it was cool and wet, and thus we would have had a lot more pine, a lot more redwood, a lot more Douglas fir and a lot less oak. And I'll show you some data on that in a minute. But this is a really nice rendition. These are some of those megafauna that we would have seen. Mammoths and mastodons, bison, horses, giant ground sloths. So fantastic menagerie. And the mammoths and mastodons, they would have been common here on the Sonoma coast. How common? Well, some of you might have been out here, but there's these sea stacks that we have that is just a little south of Goat Rock on the way up towards Jenner. 40,000 years old, and they're polished along here by mammoths who had been rolling in the mud and then scraped the same way that we see cows and other things scrape on fence posts now for long periods of time. And not just one mammoth for a long time, many, many mammoths over many, many thousands of years. Because remember, again, those mammoths have been here for hundreds of thousands, maybe millions of years, and they would have had a long time to do this.
How do you know that?
He was there.
Okay. I don't. But here's the way the study goes. Okay? The polish extends even below the surface if you excavate. Because you have to remember, over that long a period of time, through erosion and then also sedimentation, this is where the base has been changes. If it's below ground level, it can't be historic. And so what they did was they took microphotography, SEMs and different things, and compared this kind of surface compared to the smoothing that would happen by wind, or by water and waves, or by elephants rubbing against rocks that they have in Africa. Guess which matches best? So, no one was here, no one saw it. So it's still a hypothesis, but it's been tested in a pretty nice way. So this is the scene, right? You'd have been careful when you went to the beach, right? We don't know this happened. But, here you've got your saber-toothed cats, your short bears, the poor baby mammoth. This is kind of possibly what was going on. It's cool. A different place. Okay. Eventually, the climate changed one last time, and now we're at 20,000 years ago. We're almost up to the present. We're almost at the end. And so sea level rose very, very rapidly. And so that by 6,000 years ago, it had reached its modern levels. And so here's just that map again, where it was out here with the Fairlawns kind of being part of the land, but 18,000 and 14, 11, 10, 8, the coastline just kept pushing back until it reached modern about 6,000 years ago. So when we think of San Francisco Bay as it sits today, it's only 6,000 years old, which, okay, that's not short, right? But in geologic terms, that's nothing. It's very, very new. And Tomales, exactly the same. So, again, this is Laura Cunningham. This is actually, this is her impression from being down in San Francisco Bay, but it's very similar to what Tomales would have looked like at that time in terms of kind of as the sediments filled in, sea level came up, bird life filled in here. We can really imagine this landscape. And so in the last 10,000 years, we've seen the last changes, and those happened to the actual landscape trees, that sort of thing. And so this picture's not from here, but it's a great one of oak woodlands, and we all drive around. We know oak woodlands are really common. They're very characteristic of California, and they're very recent in terms of kind of the landscape. Because I'm going to show you another really terrible squiggly line, but these lines simply represent oak pollen that has been found either in lake deposits from Clear Lake or in ocean deposits off Santa Barbara or the Northern California coast. And what you notice is that right there, there's no oak pollen. Where were they? It was mostly pine all along the coast here. It wasn't this nice interior with oaks and grass. It was something very different. My own hypothesis on this is that they persisted in very small populations on south-facing rocky steep slopes that would have been dry little microclimates where they could persist. Because as soon as the climate got warm again, this is the last 10,000 years, that's the end of the glacial, the beginning of what we call now the interglacial, the Holocene, they came right back. So they had to have been there in small populations. And as soon as the climate was good, they came back. This is us. This is the last interglacial. It did it then too. And so this landscape, the trees that we see, you go from oak woodland to maybe to mostly pine forest and back to oak. This has repeated itself. And so we see that in the trees that we have. And not just the oaks. This is another interesting one. Think about redwoods, okay? A couple of things to note on this map. First of all, we all know that they sit very close to the coast within the fog belt. But they didn't used to. They used to be all the way out in Nevada and in Idaho and a whole bunch of other places. Which tells us that if you go back 5-10 million years, maybe not even that long, those places were like the coast. They had to have been, otherwise the trees couldn't have persisted. They had to have been cooler, wetter all the time. But the only place where that climate exists for them today is hugging along the coast here. And so we have what I would call, if you live in Tomales, you live in a Miocene climate, okay? You're pretty safe, it's been here for a long time, all right? And it's very strongly modified by just being on the water with this cold upwelling that creates the fog currents. The other really kind of interesting thing on this is it's virtually none out on Point Reyes. That's because of the geology. The geology changes, and what you get there is bishop pine. Because bishop pine grow really well on the granites that are there because they don't require much in the way of nutrients. But they're also coast huggers. Okay? All the closed coast pines also live there. And we don't have as good a fossil history to know where they were before, but what we do know is that they require this very unusual climate that only occurs right on the coast. And so they're relics. They're relics of a previous time. They used to be much wider distributed, but now they're really just in our neighborhood. If you go up on the ridge, the Linus Ridge, and you're looking back, or you're up here, you note that here's Tomales Bay. There's this dense kind of canopy of pines over here. Over here it's grassy, and it's with some conifers in here and oak woodlands. Two things going on here. First, it harkens all the way back to that geologic map, the one that didn't fall down, that showed the pink on one side, the granites, and the marine Franciscan on the other. It's expressed in the vegetation. This sharp divide that we think of as geologic, it's also a biologic divide because of the soils. And to a lesser extent, some of the climate, just because it gets a little drier here, a little less than on the other side. So, I'm going to leave us with this one, where we've got this great view looking back, and it harkens back to this book, Island in Time, published in 1962, which we had as a coffee table book in my house when I'm growing up. And all the time I'm thinking, oh yeah, what they're talking about is that this peninsula is continuing to move north and eventually will be separated and be an island. But guess what? That's its past history too. It was always out there, kind of part of the ocean, and it's just attached here for this short period of time that we get to live in and enjoy and look at. But it's just, what we're seeing is just its point in time now, where it came from and kind of where it's headed. I'll leave it there. Thanks.
Great talk. One thing I guess I'm always interested in, and you mentioned earlier, is that the rolling hills here are smooth. And I love this feature of our landscape. So can you elaborate a little bit more about their origin per se and how old they are? Are they younger because of these sediments you've been talking about?
I love the question. I don't have a good answer. There's a few places that are, I'm thinking particularly like the Petaluma Gap, where there are some softer hills here than if you go north or south. There's only a few places where you get that. You get that when you go down around Salinas again as well. I think they're simply tectonic depressions of marine sedimentary rock that's a little more erodible, that has kind of created these little dips and resulted in this softer landscape. It doesn't show up this way in that many places. Most often the hills are much more dramatic. Even though we think of them as rolling, you get down and look at them, and they're pretty steep. And so I think it's just, and I'd love to know a little bit more, but I think it's just this kind of depression in the rock underneath that's kind of lowered this whole area to make these little gaps, which only show up in a few places in all of the coast, and sedimentary rock that's just a little more erodible.
And after we see it from space, we actually see different productivity of these regions because of it.
You'll have to give that talk.
So. one quick point. I grew up in Oakley. My mom grew up here, but I grew up in Oakley. And my dad said when they dug wells, they find redwood trees.
Yeah.
And there it's just desert, essentially. So it really shows how things have changed over time.
Yeah.
Where? This is Oakley, East Contra Costa County, the Delta region, where the Sacramento rivers meet. So redwoods are there.
Yeah.
Maybe.
About how much more sea level rise can we expect in the next 100,000?
Well, that's actually a really great question, because the sea level rise that we would anticipate seeing now has more to do with the current kind of climate change accentuated by changes in the carbon dioxide in the atmosphere and retention of warmth than it does with just natural, okay? So we're seeing it coming up. If you look at the long-term trends, we'll be heading towards an ice age, okay? That ice age is not going to catch us before sea level goes up. But
Before the ice age, when all the ice melts.
if all the ice were to melt, I don't think so. That's a lot. I mean, but I think this is wrapped up with the whole notion that if you can get off carbon, right, it's going to get up. Man, it's a good one. If you can get off carbon, right, then you're going to slow that rise down. At the rate it's going, it's not coming up nearly as fast as it was when the Holocene started at the end of the ice ages caused by climate. So what the projections show us going up 6 inches to a foot by 2050, and maybe several by the end of the century, and it's a lot.
I'm talking 25 or 100,000 years.
In 25 or 100,000 years, it's going to go back down,
Okay.
because we'll go into another ice age.
So between going back down and it's going up, there must be a peak somewhere.
Yeah, I know. Yeah, I'd like to know the answer to that too.
How much was the sea level rise the last maximum? The previous Holocene?
Oh, during an interglacial, how much higher has it been?
Yeah, previous. You showed lots on that chart, going up and down.
Yeah. But since the ice age, in the last 2.5 million, it's only been above a few times, and in that, it's been as much as a meter or two higher. And naturally, before that, it was 10s, 20s meters higher. I mean, if you melt all that ice, you'll go up 60 meters. So there's a lot.
60 meters.
That's a lot. It's a lot of water. Yeah.
Thank you.
What's the history of the cypress tree in California? I understand that it used to be, kind of endemic here.
Well, it is endemic, right, the cypress, and they are very similar to the closed-cone pines in that they are relics that are isolated along the coast and would have had a wider distribution. But again, I have not seen a good fossil record of those to know exactly what their distribution was. But cypress are common in cypress and juniper, and those are common in dry climates. There's no reason why they couldn't have been much more widely distributed in the past when the climate was milder at that time. So my guess would be it's similar to closed cone pine, but I haven't looked at that one specifically. Yeah.
You use the terms pushing and pulling.
Yeah.
And when I think of pushing and pulling, it begs the question that there's a force pushing it and a force pulling it.
Yeah.
What are these forces?
So the pushing force, and what we're talking about here is plate tectonics, where the plates are moving apart. The pushing force is convection of magma deep in the earth, and as it rises through in different locations for reasons that aren't always entirely understood. Right? When they get up, essentially the force of that magma coming up is the push. Okay? The pull is actually a suction, where once it starts subducting and going down and melting, right, it weakens the kind of resistance and allows it to kind of pull more in. And so there's just a little subtle push here and a little pull there.
What's the difference between the ocean going down and the land going up?
Okay, so one is controlled by the volume of water on Earth versus ice.
Is fixed.
That's a fixed volume,
Yes,
right?
fixed volume.
And the rising is both isostasy and I'll get to that.
Okay.
Both isostasy and tectonics, okay? And so, sorry. So tectonics is simply that force of the continents pushing each other and lifting the Earth. That's most of what's going on here right now. But there's plenty of other places on the planet where if they were under ice, the weight of that pushed the continents down, because the continents themselves simply sit on a kind of plastic, semi-mobile surface underneath, so that as you add more weight, it's a bit like if you had a surfboard sitting on the water, right? When you put more weight on the top, it goes down. When you take it off, it comes off. The continents are the same. And so in some places, they're actually rising simply as a response of having had too much weight on them. So if you have something like the Sierra Nevada, that's a very thick mountain range, it's pushing the Earth down. As it erodes, it springs back up. So both forces are going on, this kind of natural response of the Earth in relation to weight above it, as well as sea level coming up and down based on climate of melting of ice.
Have you been to Ephesus?
I have.
And you stand in Ephesus, which was a seaport,
Yeah,
and you can't see any water.
that's different.
That's different.
That's erosion. That's infilling, okay? So sea level there has not changed significantly, but the,
The land has gone up.
no, the land hasn't gone up. Inland, where there's been extensive agriculture, that has come down, and so that's simply filled in. So it's kind of like if you go around San Francisco Bay, it's much smaller than it used to be. Part of that's natural erosion and sedimentation. Part of that is us filling it up so that we can build. Okay? Same types of things happened at Ephesus in terms of erosion of material coming down, filling those shallow embayments, as well as material getting added. It's kind of it's the same story of coastlines all around the world where Pompeii is the same thing. All of the Italian coastline. It's a combination of erosion, kind of infilling, because that, let's face it, the water level's not that high. It's relatively easy to fill in. Once you fill it in, hey, I can farm this, and that's good. Let's keep going. And so that's happened. And that's all happened within the last
1,000 years, 2,000 years.
I'll go out on a limb, I'll say 4,000, but it's probably, mostly in the last 2,000.
All right, okay. I'm sure that,
I can go on forever, but I'll stay here.
But you're welcome to buttonhole stuff. When I release everyone else here to their own goods, so we do want to give you a gift for having come out and given such a great presentation.
Thanks.